So today's song that we have for you is the old school Pokemon theme song, and we're covering the topic of electricity.
Pokemon style.
Yep, they even wrote a book about it.
The complete Pokemon physics guide.
Yep.
Now available in stores.
There are 3 rules to remember. Opposite charges attract, like charges repel, and any charged object attracts some neutral objects.
To remember these, think of a magnet. The north sides are repelled, but the north and south side attract, like plus and minus, and a neutral object, like a nail, is also attracted.
Let's talk about induction. Keep in mind a ground is an infinite source of positive and negative charges. Grounding makes a particle neutral.
I guess you could say that it got grounded.
Cat, why? Go.
Let's do some examples. If you have a particle that's neutral and you bring a negatively charged object near the neutral one, the positives will be attracted to the negatively charged object and rearranged like so. If it's then grounded, the negatives will leave and the particle becomes positive. Let's try the next example.
So a neutral object and a positive rod is brought near it. Then it's grounded. What happens to the particle? The particle becomes negative. The positive rod makes the neutral particle negative, and once it's grounded, the positive charge will leave, making the particle negative.
Also, remember that charges want to spread out, like that annoying person on a flight or in a movie theater. So if a smaller particle is attracted to a larger one, some charges will move to the smaller side, with most staying on the larger one.
Let's talk about circuits. Circuits can either run in series or in parallel. And with these pictures, they are not trying to scale. On the parallel one, the bottom one should be a little bit smaller to show the positive and negative side. But in series, current is always constant, whereas in parallel, voltage is always constant. So using the formula V equals IR, everything can be found. This concept is fairly straightforward, but can get complicated when circuits in series and in parallel are combined. Let's do an example.
Current runs from positive to negative, and the positive side is always on the longer line. In this case, the current runs clockwise, and we're given a voltage of 5, and these two resistances both equal to 2. You can find the total resistance of these two here by using 1 over R equals 1 over R1 plus 1 over R2. If you add these two together, since they're in parallel, you get a total resistance of 1.
Use V equals IR to solve for I.
Current is equal to 5 over 2. Then you have to redraw the circuit so it's just in series. In series, the I is constant, but be careful. In this case, the current is split in half over these two, so your total current would be 5 instead of 5 over 2. Since the current is known along with voltage, you can find the resistance of this light bulb here. Set it up and solve, and you get a resistance of 1.
Often there are questions about brightness. Just know that brightness is equal to power. The more power, the more brightness. Here are 3 of the most common power equations. P equals I squared times R, P equals IV, and P equals V squared divided by R.
The last important concept is this formula chart, and knowing how to go back and forth. In scalars, it matters whether it's positive or negative. This concept is just knowing what the formulas are and how or when to use them.
Today's snack time is Pokemon fruit snacks. And we got a whole bag of them. Look how cute the packaging is. It's very nice. Here you go, Julia.
Thank you.
My favorite one is the red one. They are all shaped like Pokemon, and I'll show you that. This is what they're supposed to look like. They're very cute. And if you get yourself one, take the box top to the school and save money.
Free advertising.
So here we have a practice AP problem involving circuits, and this is the all or nothing problem. The first question is to calculate the current in bulb A. If we're able to rewrite these light bulbs in series with A, the currents will be equal. So if we're going to do that, we first have to find the total resistance of these 2 light bulbs. So 1/6 plus 1/3 equals 1 over R, giving the total resistance as 2. If you redraw a circuit, it would look like this. Now for the new circuit, the total resistance is going to equal 1/3 plus 1/2 equals 1 over R. And this is shown right there. And we know for that the voltage is 9. So you can set up the equation V equals IR or 9 equals 5I and solve so we get the current is equal to 1.8 amps.
To find which bulb is the brightest, we don't need a math test. We're just going to use the power formulas P equals IV. Right now, we don't know the individual voltage, so we'll have to do a little more math. For bulb A, we know the current and resistance, so we can find the voltage. A's voltage is 5.4. Now that we know the voltage and current, we can multiply them together to get the power as 9.72 watts. I'm going to read this nice and slow for Julia's sake. For bulbs B and C, we need to go back to our first diagram. Here they are in parallel, and we know voltage is constant when bulbs are in parallel. If we take the total voltage and subtract A's voltage, we get 3.6 for both B and C bulbs. We can then calculate the current for each bulb and end up with 0.6 amps for B and 1.2 amps for C. Then we calculate power and obtain 2.16 watts for B and 4.32 watts for C, making A the brightest. I guess you could say it's the brightest bulb in the drawer.
If switch S is opened, you get the exact same circuit minus the C bulb because no current will flow through this part.
That's because switch S left bulb C and took the kids.
The voltage will stay at 9 volts, but the total resistance changes to 9 ohms because A is 3 ohms and B is 6 ohms. When plugged into the formula, the total resistance has changed to 9. You can solve for the total current and get 1. Since we're in series, the current at A and B is 1 because current is constant in series. Now that we know the resistance and the current for each of the light bulbs, we can find the partial voltage for each of them. For bulb A, it's equal to 3 volts because 1 times 3 is just 3, and for B, 1 times 6, so it's 6 volts. Now that you know the current and voltage, you can find the new power. For A, it's 3 watts, and for B, it's 6 watts. Again, 3 times 1 is equal to 3, and 6 times 1 is equal to 6. So now when you compare the new powers to the original power, A's original power was 9.72, and the new power is 3. And since 3 is less than 9.72, you can therefore say that the correct answer is that it decreases, but you can also think of this conceptually. Since the resistance goes up, current has to go down, and R and I have an inverse relationship according to the formula V equals IR. For B, the power is decreasing since a higher current is flowing through B. Note that for the overall current, the number has decreased, but current has increased through B. And for C, there's no current flowing through it, since therefore there's no brightness, so it decreases.
Do you know why you're here?
No.
Well, the last physics test. You didn't do so well, did you?
Well, no.
Why do you suppose that is?
I don't know. Maybe I didn't study?
Well, that surely would be a problem, isn't it? I believe you forgot one equation. Do you happen to know which one that is?
I can't remember it.
You're lying.
I'm not!
That's the face of a liar. Quit smiling at me. You know what you did. You forgot V equals IR. Told you, Brian. It's a very serious crime. Unfortunately, it's the death penalty.
So that's all we have for you today on electricity. And I guess the most important thing to remember is
V equals IR. Pikachu.
I wanna be the very best.
Let's do some examples. If you have a particle that's neutral and you bring a negatively charged object in,
It's just gonna be a random dog in there.
This is what happens if you don't remember V equals IR.